Welcome to this third session of our ongoing popular mathematics lecture series. Today's speaker is Professor Diane Hoffoss from the University of San Diego, California, and she is a PhD from University of California, Santa Barbara, and she is an expert in 3D manifold hyperbolic geometry, flows, and foliation. And she has got a lot of interest in popular mathematics. You may find her contribution also, which have appeared in well-known journals and many other publications covering these areas of mathematics. And she has worked at many other in many well-known prominent universities like Reese University and University of California, Santa Barbara. And she has also been associated with the mathematics, computer science, and communication research division of Baylor, which is formerly Bell's Lab. So it's my pleasure to have Professor Hoffoss with us as a speaker in this session. Professor Hoffoss, I'm thankful to you for accepting our invitation and agreeing to speak in this session. I'm sure that your talk will be interesting, and there are a lot of people who are joining us will have a curiosity after this talk to know more about the topics that you are going to talk about. So I once again express my thank on behalf of the Department of Mathematics and Computer Science of Baubanarsidas University, and I also once again welcome all the participants in this who are joining us in this session. So again, at the end, I will request all the participants, if you have any question, you can type it in chat, because we will we have put all the participants in mute mode. You will not be able to speak, use your audio. So you can type your questions in and over to Professor Hoffoss.
Hello, good to see everybody. Let me get this screen shared. 1 second. Okay. All right, can everybody see my screen here?
Yeah.
Yes, okay. Okay, so thank you so much for that really warm introduction. I'm so happy to be able to talk to you today about something that's been very dear to my heart over the past couple of years. And I was very excited to receive this offer, this invitation to speak here. I appreciate the invitation, and I'm very honored. I wanted to tell you about this experience I had in 2018, creating a large mathematical sculpture and bringing it to Burning Man. And I think probably I should start with some questions which you probably have. And maybe the first one is, what is Burning Man? So Burning Man, there's as many answers to that question as there are people who go to Burning Man. But one way to explain it is it's an event. It's a week-long event, which it's an experiment in a temporary community. It takes place in the desert, and it was founded in 1986. It was a very small gathering organized by Larry Harvey and Jerry James. at a beach near San Francisco. And then it grew, and we ended up moving it into a desert location where there was more space in Nevada. And the community is based on 10 principles, and I'll just tell you a couple of them. One principle is radical inclusion, and what that means is everybody is welcome, everybody is included in everything. And so you're meant to feel comfortable to come up to any group of people or any camp or anything and introduce yourself and come in. Everybody's welcome. Also, leave no trace. That's another strong tenet of Burning Man. And what that means is when you come to this temporary community and you bring things, you take everything with you. So even splinters of wood, even every tiny little thing that you might have dropped, you bring it with you. Another important principle is gifting. So when you come to this community, you're meant to come with a spirit of giving. And many people will bring physical gifts to give. But some camps will say have a day where they'll serve everybody grilled cheese sandwiches. Some people will bring art projects for people to enjoy. And some people will just be there ready to help if somebody needs help. So, but one principle that really stands out for me is participation. So there was an exhibit not long ago at the Smithsonian in Washington, D.C., based on Burning Man art, and it was called No Spectators. And that's because when you go to Burning Man, you're not meant to stand back and watch, you're meant to become part of things, participate. So this will come into play in the later part of my talk. Okay, so Burning Man takes place, here's an overview of the location for Burning Man. This is Black Rock City. It all takes place within this Pentagon, and even the Pentagon disappears at the end of the event. So it's so everything that you see here is temporary. It's a city of about 75,000 people, and the participants live in this semicircular shaped area. This is where everybody's camp is. And then let's see, let me try to orient you. So Burning Man, there's a man, and the man that gets burnt is right here at the center of the circle. And the way they orient the way they sort of orient the city is to have that be the center of a clock. And then straight up here is the temple, that's 12 o'clock. And so this is 3 o'clock, 6 o'clock, 9 o'clock, and then all the radial streets have addresses based on the clock. Let me just get a little more orientation. This is Center Camp at the 6 o'clock, and at Center Camp there's performances. You can buy ice. Now you can buy coffee, but that's really all you can buy at Burning Man. Everything else you bring in, and then you also bring out. Okay, so another thing that Burning Man is, and this is what really is important to me, is it's an enormous sculpture garden. So one thing I didn't point out to you is all these other little black dots everywhere. Up here, this area is known as Inner Playa. This is Deep Playa. And every one of these black dots is a large sculpture. And they're everywhere. There's hundreds of them. And so it's just a glorious sense of a discovery that you have when you ride around and run into these large sculptures that are fun and beautiful. And so I'm going to give you a sense of the scope of this, the size of this city. I've told you the number of people, but the land area is about 18 square kilometers, so 7 square miles. And I looked up the land area of BBDU, and I think this Black Rock City is about 45 times that size, just for perspective to that. So it's pretty big. This distance right here is 3 miles or 5 kilometers. You need a bicycle to get around. And okay, so that's what Burning Man, that's where Burning Man takes place. This is Black Rock City. Another question you might have is, why did I create a sculpture to bring to Burning Man? Well, so I'm a math professor, and I've been a professor for 23 years. And one thing that I've noticed is that, at least in the United States, there's quite a lot of misconception about what a mathematician does. when people find out that I'm a mathematician, they'll say things like, oh, what's the biggest number that you know? And, or oh, you can probably calculate the tip when we go out to dinner. And, you know, that's the thing that I can do, but we know that that's not actually what mathematicians do, what they're interested in mostly. And so I've been interested in helping people understand the true nature of mathematics, what kinds of problems we work on, what sorts of things we think about, what attracts us to this beautiful field, why we think it's beautiful. And independently of that, in 2016, I went to Burning Man. I really like lights, and I've got a lot of lights behind me. And a friend was at my house, and he said, "You've got so many lights in your house. You might really enjoy Burning Man." And I just went, and I was really struck by the openness of the people and the warmth. And but I especially love their curiosity, sense of play and experimentation and open-mindedness. And then I also noticed a lot of the sculptures at Burning Man are mathematically based. So these are some sculptures from Burning Man. Up here, the upper left is, this was the temple the year that our project was there. It's this beautiful spiral. The upper right, this is, you know, stacked truncated cubes by Kirsten Berg. On the lower left, this is an icosahedron, but there's this beautiful patterns carved into it, and then they're stereographically projected down onto the ground. And if you spin this icosahedron, then the pattern shadow patterns on the ground also move. Over here is a project by Fold House, where these are origami mushrooms, and if you step on the panel, they'll compress or stretch. So this is part of the participation interactivity I was mentioning before. One more I'll briefly mention is this bioscope by Matt Brand. So he's another mathematician. If you look, so each of these truncated tetrahedra, if you look up from them, this is what you see. There is reflective. So you've got these reflection groups, and you can put different things at the top and see what the reflections look like. So anyways, there's a lot of mathematics at Burning Man, and I thought to myself, this might be a really good audience to try to communicate sort of the joy, the beauty, the excitement, the true nature of what mathematics is. So, so I decided maybe I could try to represent some version of the mathematics that we think about in some physical form, some beautiful physical form, and bring it to the public at Burning Man. So that was the plan. But it turns out that I'm not a natural artist. And so it took me quite a long time to come up with an idea that I felt comfortable making a sculpture about. So I thought what I really needed to do was just take a year to gather some ideas, to get some experience. So I looked around and I found this project called the Journey Project. And before you knew it, I was the lighting artist, because I love the lights, and the software lead. And this is what the Journey Project looked like. So it's this coiled torus, and there was an LED light show and so on. And throughout this process, I really learned a lot. I learned what goes into creating such a large scale project. I learned about volunteer culture. I learned about the challenges of constructing a large sculpture in what's really a very harsh environment. I learned a lot about programming LED animations. And then I also developed a very healthy attitude towards failure. And so with all that behind me, I was ready to do something, but I needed a good idea. So where did the idea come from? Right around this time, or a little bit earlier, we had a new faculty member in our department named Sethian Devadas, and he's just a joy. And I thought, oh, well, maybe he would want to join with me on this project and see what we could do. And he was very excited about it, of course, because he seems to just love everything. And so he suggested that we should try to try to represent an unsolved math problem, because he noticed that many mathematical sculptures and mathematical art is based on centuries old mathematics. He wanted to get at something new. I love that idea. He was teaching a geometry class at the time. And so he set an assignment for this geometry class to for each teams of 3 people to come up with a sculpture to bring to Burning Man. And there were 3 requirements. It had to be based on an unsolved problem in mathematics or a recently solved problem. Had to be interactive, this participation thing I was telling you about. And had to somehow refer to the theme for Burning Man this year, which was iRobot. So 5 teams submitted their proposals and we watched their presentations and we chose one to pursue. And this is the one we pursued. It's about an unfolding dodecahedron. So the student team, Jordan Abushla, Nick Bale, and Eugene Wackerbarth, they proposed this unfolding dodecahedron as their sculpture. And the way it fit the requirements, it referred to the unsolved problem. It referred to Durer's unfolding conjecture, which we'll talk about. The interactive nature is that the participants themselves should be able to unfold the dodecahedron. And the iRobot, their description refers to a connection between humanity and technology. So we love this idea. And we added a little bit to it. We added, for example, on the outside, we added this sort of character Rain from the movie The Matrix. Maybe you've seen that movie. And on the inside, we put mirrors. And so this is what the model ended up looking like. This beautiful computer model was made by a student named Quinn Pratt, who is good at all things. And I was very glad to have him be able to do this. So this was our goal. This is what we were setting out to achieve. I want to tell you about a little bit more about these 3 themes, especially about the math problem. This is a popular math talk, and I'm really wanting to describe like how I tried to make math more popular, I guess. But let's just talk about what this problem is. So Durer's unfolding problem. So Albrecht Dürer was an artist. He was a painter. He was a printmaker in the 1500s. And he became very interested in perspective and representing 3-dimensional objects. And he had studied with the Italian masters about perspective and so on. And he wanted to somehow communicate polyhedra through his prints. But that's a 3-dimensional thing that he wanted to represent in a 2-dimensional way, and he sort of struggled with ways to do that. And this image is a page out of his notes. So these are all different representations of an icosahedron. This one, is sort of stretched around to be flat. But this one over here in particular, this is the sort of thing that we're going to be talking about today. So this is an unfolding of the icosahedron. And this is a really good flat representation, because if you were to cut open along this and then fold at these boundary lines, then you could reconstruct the icosahedron from the flat piece of paper. So then the question is, can you always do that? Is it true that for every polygon, every polyhedron that you could come up with, there'd be some way that you could cut along the edges and unfold it so that it laid flat, but importantly, it lays flat without overlapping itself, because if it overlaps itself, then you can't really, you can't treat it as something to print and then reconstruct. Okay, so that's it. That was the big question. And well, in fact, it's not true for every polyhedron. There are non-convex polyhedron that it's not true for. But it's still an open question. Is it true for convex ones? So, well, let's just think about how could you even tell for sure that it was impossible to cut open a polyhedron to have all the faces lie flat without overlap. So let's just look at this non-example. It's not an example because this is not a convex polyhedron. So I haven't found a counterexample to the conjecture. This is just something that's nice to talk about to get the ideas solidified. So it's not convex. Most of you know what convex means, but I'm just going to say it in case anyone doesn't. So it's not convex because there are 2 points in this polyhedron, let's say a point here and a point here, such that if you connect them with a straight line, part of that straight line will be outside of the polyhedron. That's what makes it non-convex. So a convex polyhedron, that can never happen. But so for this non-convex polyhedron, how do you know that this does not have an unfolding without overlap. Well, this face right here, this face would have to lie flat somewhere. And once it did, there would be only the size of this small square's worth of space left to fold all of these 5 squares into somehow. And that can't work. There's just too much area to put down into that one small square. So, so in any case, this is an example that it's not possible to do, and it's pretty easy to see why. I didn't mention in the definition of the conjecture, but the assumption is that once you've unfolded it, that it's still connected, that you don't just, because you could just cut every single face off separately and then that would lie down flat, but that's not part of the problem. Okay, so how will we determine this either way? So, well, what you always do if you're trying a new math problem is you start with some examples, try to see what you can do. So let's look at the platonic solids. So each of these platonic solids, each of these surrounding platonic solid does have an unfolding without overlap. And these are the images of examples of those. In fact, it's a little stronger because in every single unfolding of each of these happen to not overlap. So that's good news. They're all good. And but what do I mean by every single unfolding? How many of them are there? So if we're going to take an arbitrary polyhedron and we want to sort of check some unfoldings to see are there any that don't overlap, we should have a sense for how many different unfoldings we're really going to be checking. So let's think about categorizing those. So this is one example of an unfolding of a tetrahedron. And maybe you can imagine this bottom face could be the center face. And then each of these side faces unfold to these corners of the triangle. That's one way to do this, but I could have thought of this side face as the center face and unfolded based on that, or this side face or the back face. So what that means is this really represents 4 different unfoldings. But we're just going to call that one unfolding, sort of one unfolding type, just to simplify things. Well, so then for the tetrahedron, there's 2 different unfolding types. There's this one that looks like a triangle, and then there's this one that unfolds like a parallelogram, and those are the 2 different types that you get. So we've got 2 different types of unfoldings for the tetrahedron. It's also known for the cube. So for the cube, there's 11 different, fundamentally different types of unfoldings. And for reasons of duality, for the octahedron, there's also 11 different types of unfoldings. So I wish you were able to talk, because I'd love for you to make a conjecture about how many unfoldings there are, just watching this pattern, how many unfoldings there are for the dodecahedron or the icosahedron. So just get a number in your head. And was it this number? Probably not. So most people will guess, oh, maybe 100, maybe 200, something like that. But it's 43,000. It's really a lot of different possible unfoldings. You can see that this problem grows tremendously as the number of vertices grows. So, so it's a tough problem. And so do mathematicians think that this conjecture is true or false? Well, interestingly, there's actually very convincing evidence on both sides of the question. So some evidence for it is that there's a vast number of polyhedra that people have just sort of by brute force, computer programs, trying different things, have found unfoldings that don't overlap. Okay, so there's a whole bunch of examples that we know work. Also, some other partial progress. Alexandrov in 1950 showed that if you don't restrict yourself to cutting at the edges, if you allow yourself to cut through the middle of faces, then there's always an unfolding for a convex polyhedra. And here's how you do it. You just choose some point on one of the faces, and then you draw lines connecting each vertex to that point. And then you cut along those lines, and then that will give you an unfolding with no overlap. Okay, it's not the same problem, but it's a related problem, and that works for all of them. But also some evidence to the negative. So Diane and O'Rourke in 2007, they showed that if you take just an arbitrary polyhedron and you choose an arbitrary cutting along the edges to unfold, that the probability that that random unfolding has an overlap, that probability goes towards 1 as the number of vertices grows. Okay, so it's more and more and more likely that the more complex your polyhedron gets, it's more likely that a random cutting will have overlap. So it's feasible that there's a large enough polyhedron for which there's none of them will fail to have overlap. This is an important result by Gomi, 2014. So what he did was he showed that if you have a polyhedron, maybe it can be unfolded to without overlap, and maybe not. But if you stretch it in a direction, in fact, he showed that in all but, as long as you're in general position and stretch it in just about any direction, then there was an amount that you could stretch such that the stretched polyhedron could be unfolded without overlap. And so if you see, this is an example of this particular unfolding did have overlap, but after a little bit of stretching in this direction, we've resolved the overlap here. This is not to address the original problem because the geometry has changed, but it does show that it's not a combinatorial problem. It's not a problem with the number of faces, the types of faces, or the locations. It's really a geometric problem that we're thinking about. So there's no combinatorial obstruction to this thing being true. Okay, so we just really don't know. The question is very open either way, and so that's what makes it kind of exciting. That's what mathematicians love is a big puzzle like this where evidence keeps coming up on both sides, and it builds the suspense. Okay, I'd also like to tell you about another theme of this project had to do with the shape of our universe. And when I say shape of our universe, I mean two things about it. First of all, the curvature, and second of all, so it's the geometry, and second of all, the topology, or the way that it folds back upon itself. So I'll talk about both of them. So when I say the curvature, what I really mean is the geometry. And so what are the possible geometries? Well, there's 8 different geometries, possible geometries for three-dimensional space, but 5 of those geometries have a preferred direction, meaning the way you measure in one direction is different than the way you measure in the other directions. And we don't suspect that the universe has a preferred direction to it. So we only consider the 3 for which that's not true, the 3 for which all directions of measurements the same. Those are called isotropic. And here are those 3. Well, this is the 2-dimensional analog, but here are those 3. There's with positive curvature, like the geometry on a sphere. There's negative curvature, like the geometry on this hyperbolic plane, or there's exactly 0 curvature, Euclidean flat geometry. There's analogs for those in 3 dimensions, and those are the 3 options for us. And one thing that's pretty cool to notice is that if the space has spherical geometry, then it's definitely finite. So if our universe happened to have spherical geometry, we would know we lived in a finite universe. On the other hand, if it had hyperbolic or Euclidean geometry, then it could be finite, it could be infinite. We wouldn't know. So you might be thinking, wait a minute, why would you think that the universe how could it possibly be finite? When I go outside and look, I can just see forever. I don't see the wall. How could you even consider the possibility of being in a finite universe? So I want to just try to describe to you how you might think that could happen. So let's just think of, here's a little spaceship. Here's a spaceship, a person in a spaceship living in an incredibly small universe. This is this entire size of their universe. There's a couple of stars, there's a couple of planets, and that's all there is. So I wonder if you've ever played a video game where when you, there's a game called Asteroids that I've played before, where if you sort of go off one side of the screen, you come back on this side, or if you go off the ceiling, you come up from the bottom. So, well, imagine that's what their universe is like. So in other words, if he were to fly this direction, he'd come back in this side. Well, his line of sight would do the same thing. So if he looks straight ahead, he would see the back of his spaceship. So that would be his view. And if he looked upward, he'd see the bottom of his spaceship. If he looked downward, he'd see the top of his spaceship. If he looked back, he'd see the front. If he looked to the upper right, he'd see, in fact, any direction that he looked, he would see a copy of his spaceship. To him, though, he wouldn't look at my spaceship everywhere. He'd think, wow, there's a lot of spaceships in my infinite universe. But if he tried to catch one of those spaceships, he never could, right? Because if he tries to go from here to this next one, this copy will also move forward because it's really just the same spaceship. Okay, so I was just trying to give you a feeling for how it could be possible to be finite. So is this true? Well, we don't know. So in the early 2000s, there was a satellite called WMAP satellite, which was taking data from the Big Bang. So you might wonder, how can we take data from the Big Bang? Because that happened a long time ago. But in fact, you know, that light takes time to travel. And so as you look a distance, really you're looking backwards in time. And so if you look far enough, then you're seeing back far enough in time that you can see back to the Big Bang. And what does that look like? Well, at the time of the Big Bang, or really just right after the Big Bang, it was just this plasma, this opaque plasma. So that's as far back as we can see. And that's called the cosmic microwave background radiation. And that's the thing that the WMAP probe was taking data from. And to try to measure the curvature. And in 2002, it seemed very likely that the geometry was spherical. And that's very exciting, because what that means is then we must live in a finite universe. And so that was really exciting for me. I thought that would be really cool. And there's not very many of these spherical finite universes to choose from. So we'd be able to maybe figure out what the shape of our universe is. So there was some like missing data, and it turned out that Poincare dodecahedral space was the spherical space which fit that sort of missing data the best. And so what would that look like? So imagine just like this spaceship living in this very small universe. Imagine if we were standing inside a very small dodecahedron and it was glued in a similar way, meaning that if I go out at the top of it, I come back up through the bottom face, maybe with a 2/5 twist. And the same thing for any pair of opposing faces. Well, if we did that, then this is what it would look like on the inside. So this is a beautiful image created by this program called Curved Spaces by Jeff Weeks. And you see many copies of the Earth, but really just like the spaceship saw many copies of himself, this is all just the same Earth. And this is showing you how space is folded in on itself. Each of these, maybe you can tell, each of these is a pentagon. It's an all right angled pentagon, which might seem weird to you because that's not possible in Euclidean space. But it is, that's possible in spherical geometry, and this is what it would look like. Okay, so our sculpture tries to simulate this idea with mirrors. It's not quite the same because it's got the reflection, but we can't actually physically build the real thing. So, so we're just trying to simulate this idea. Well, anyways, in 2014, more data came in and adjusted the estimate. So now we think that it's within 0.4% of being curvature zero. But still, that means that it could be, we're right there at sort of the Goldilocks, the boundary case. So it still could be spherical, flat, or hyperbolic. And so then the Poincare dodecahedral universe is still possible, but so is just about everything else. So we really don't know. But in any case, this is a possibility, and that's one thing that our sculpture refers to. The last thing I'll just say quickly about the iRobot theme. So the students had this lovely idea that we communicate with one another more and more through technology. And this is a really good time for me to be talking about this, because here we are now able to communicate with one another through this Zoom, through our computers, where we couldn't get together even if we wanted to because of the pandemic, and yet here we all are together. And so technology can be a great conduit bringing people together, but it can also be a wall. So maybe you stay inside more and just communicate through this wall of technology rather than having the face-to-face interactions. So the students were considering each face of the dodecahedron to be a wall of technology that people would sort of communicate through. And then folding up each of these faces would be blocking yourself inside this, isolating yourself from others, sort of one further step. So they called their project Unfolding Humanity from Technology, and we shortened it to Unfolding Humanity. That's where the name came from. So they wanted some technological images on the outside and human images on the inside. We interpreted that as this character animation. So this is the one from the Matrix, and it's a pretty well-known iconic symbol of man being connected to the machine. So that seemed appropriate. And the mirrors inside provided just infinite reflections of yourself, and what feels more like humanity than that? So unfolding humanity. Okay, now I get to tell you about the creation. This part was really fun. So I had some experience with the Journey project, and I thought, well, I'm going to need some money. So I sat down to write a budget. But then I realized, well, I don't know what I'm going to build it out of. So I need to have that before I can make a budget. And so Quinn Pratt helped me, again, the student I mentioned earlier, trying to come up with what we were going to build it out of, what the design would look like. And Lee, my friend Lee Hemingway, had been the project manager for the other project, and he sort of guided me into some other parts of it. And it soon became apparent that I needed an engineer to help. And luckily, I found one in Gordon Hoople. So Gordon Hoople is another professor at University of San Diego, and he agreed to take over the engineering of the project. So this is the structural parts, making sure that it can survive the winds. So there's 100-mile-an-hour winds that you're meant to be able to survive in order to bring your project there. And people will climb all over it. This is participation. So we really needed some solid engineering, and luckily we got that. The way we started trying to get that was to, we built a prototype face. So this was our first pentagon for the dodecahedron, and it's about 7 feet tall. And we learned a lot of things. One thing that we learned was that it's pretty flimsy at that scale, and we were going to need some internal steel to support it. So this is the University of San Diego Engineering Department engineering lab. And these are some students, Sydney and Nick. And Sydney didn't know how to weld, Nick did, and then they both learned. And here they are welding together one of the internal structures for the faces. And we had 10 of these. Top and the bottom didn't unfold, so we didn't do those. Actually, most of the welding was done by this wonderful volunteer named Sean Pennington, but a lot of the welding also happened by our students. Another thing that we needed in order to build the skeleton of it, in order to build the one-dimensional frame, we needed some very precise vertices. So the angle coming for a vertex of a dodecahedron, these are 108 degrees. And it's very hard to construct something like this. You can't just go to the store and buy something with a 108-degree angle. And if you're off just a little bit, well, what would happen? These edges are about 4.5 feet long. And so if you're off a little bit over here, that error is going to propagate to a huge error on the other side, and it won't fit together. But luckily, somehow I met this person named Wizard, who not only had built a dodecahedron before, but he was a welder. And so he agreed to weld our vertices for us. And this is what they looked like. So here's one of the vertices. We're testing it, putting it under pressure. I don't know if you can see this here. This is almost 10,000 pounds of pressure, and the welds are still holding, but this the steel tube itself is actually starting to flex. So that's 41,000 newtons of pressure. And so this seemed like it could survive having people crawl on it and so on. So this was very encouraging. Students also did a lot of other work on campus. They did, a lot more computer engineering. They did the welding. They had, some anti-rust coating, painting, glued the mirrors on. All this stuff happened at the University of San Diego. There was also the sort of skin of it, the electronics. There's more artistic components, and that happened at this place called San Diego CoLab. So we were lucky enough to get a grant from this nonprofit San Diego Collaborative Arts Project. And with that grant gave us space at this, at their build space called Collab. And they have all these wonderful tools that we could use. So this is a CNC router. One thing that we learned when we tried to make the Pentagon is it's quite hard to do this accurately by hand. And also we wanted the outside to look like a computer screen. So we had to have these holes to put characters in, and we can cut these out by hand. We couldn't possibly do that. So we learned how to program the CNC router. And here's Quinn again, running this for one of our first cuts. And okay, so here's the prototype faces in the background, but here's what else went into it. You know, we had to paint the face, and you can see the front of the face isn't so hard, but each of the sides of these little windows had to be painted individually. And here's Paul, a community member, Victoria, a USD student. This is Serena, another USD student, doing this sort of painstaking detail. We also needed some these acrylic characters, and we laser etched them on their laser bed. So here they have a 3-foot by 4-foot laser bed, and each patch of these 72 characters took about an hour and 20 minutes. And we had 2,240 total characters on the project. So there was a lot of laser running, a lot of volunteer hours for this. And these acrylic characters needed to be glued in one at a time. And so here are some students. That's Quinn again. I have so much of him, like, because he was so helpful in the beginning. And so here's Quinn and Elizabeth gluing in characters one by one on the prototype face. So what did we do with these characters? Well, so this is how we illuminated each of these characters. So this pendant that I have is an example of that. So this is just, I don't know if you can see it, this is just acrylic and it's etched on one side. This etching was what happened with the laser. And there's right here, there's an LED that's shining into the acrylic. And as it passes through without disturbance, it's clear, but whenever it hits this disturbance, that's what makes the image glow. So that's how we made these characters glow to look like a computer screen. So we needed strips of LEDs to run along the edge. And each of these strip of LEDs had to be a different length because, well, you can tell they go down the side of the Pentagon, they're shorter. So they all had to be custom soldered. Here are some of our fearless solderers helping with this project. And these two did the bulk of the soldering. This is Stephen and Ross. This is Stephen's wife, Cindy. Laurel was was measuring off sections of LEDs. Slajana was testing to see whether they worked. I also realized around now that even though I could do some LED programming, and I thought, well, these animations aren't very hard, I can do it. What I really didn't know anything about is electronic systems. And I hadn't even thought about this. So I put out a call asking if anybody could help. And luckily, the person who knew everything that I needed him to know showed up, Max Elliott. He just really saved the day. He came up with, figured out what our power needs were, came up with a wiring plan, told me what to buy. He wrote the code to get the controllers, the little computers to communicate with one another, leaving me to just write the animations, which to me was the fun part. So yeah, he was really an angel arriving at the right time. So we wired up we added the wirings to the inside, and then we started programming. So let me just show you this right here. This is what I'm talking about when I say the controller. This little patch is this right here is the computer, and it's about, I don't know, 1.5 inches. It's about this big. It's not very big. Right here is the radio. This allows this controller to communicate with all the other controllers in the project. And this is what let me turn that down. This is what the animation looked like from the inside of it. So here's some stats. The project was 2 tons, so that's about 1,800 kilograms of steel, wood, and acrylic. 12 feet tall, so 3.6 meters tall, 2,240 acrylic windows, 16,000 LEDs, programmed by 25 of those little computers, 6,500 person hours, about $45,000 of grants and donations. So it ended up being a pretty big project. So I'll tell you quickly about the build. So we got this desolate patch of lake bed. This was where we got to put our project, and I'm sort of pounding in the stake of where we get to set up. We got some help digging some anchors in so that we could anchor the project down because of these winds I told you about. And over here, this is a trench to put the cable in, the power cable in over to the generator outside of the picture. But then everything else was human powered. So, oops, sorry. Everything else was human powered. So we just carried things around, built the scaffolding, put it up. Oh, there's the animation. So, so we just built it by hand, and then we put the faces on. These faces are about 250 pounds, so 110 kilograms. And it took a lot of people to lift it. We're trying not to scratch it because the mirror's on the inside. Anyways, all human built. We added the panels to the outside. And then it was time for Max to start doing the wiring. So I don't know if you can see, but right here, this is the wire that comes from the generator, the power, and then he's about to set everything up. Connecting some LEDs at the top. And then we get to celebrate. So this was our first time of seeing the project, and it was very exciting. We hadn't had a chance to assemble it before we came out, so nobody had seen it. And here I'm peeling off the protective plastic off of the mirrors so we can see it. And here we are, first view of it. Everybody's so excited to be done and excited about how it looks. And that was a really great moment. We were supposed to finish by midnight. We ended up finishing by 7:30 p.m., which was great because I thought we were pushing it. So, well, how did it come out? What did it look like? It looked like this, and it was just glorious. I just get goosebumps when I see it because it really exceeded what I was hoping for. It was just stunning to me. I loved it so much. And so here's just some images that friends have sent me. There's a picture of it. Here's people interacting with it. So that she's using a chain hoist to pulling on the chain to close the face very slowly. People are getting into it and closing themselves up with it. Actually, we set the project up so we could open up all the way to be true to the mathematics, but in fact, we couldn't do that here because there was too much wind when we were there. So, but I'll just show you this image from somewhere else. True to the mathematics, it does open up all the way. The reason these aren't open up is because we needed to have it to stay connected. So this part is connected to this part and it can all open flat without overlap. This is the view from the inside. So this is sort of all the reflected views to try to look like that Poincaré dodecahedral space. We had a light show that was animated. I tried to make it look space themed, like twinkly stars or comets, or this. I just thought this color of blue felt space themed to me for some reason. And so here's Brianna closing us up into it. So it was really fun on the inside. People were visiting at all times of the day. So this is in the early evening. This is about 1 a.m. This is 5 a.m. This is sunrise. There's people there. Here's midday. Somebody's there. Late in the afternoon, people are still there. Not as many people during the day because it's quite hot. And people tend to sort of stay in their homes during the day and then come out at night. The thing that I loved so much about this project is it inspired joy in people, and I hadn't expected this. I was sort of testing my math theory, and I didn't even really think of how I would feel to see people so happy about the project. So you can just see on their faces, they're just excited, and it was beautiful. It also inspired play. So these people are treating it like a spaceship. They're pulling it closed and they're counting down to blast off, and other people treat it as a time machine or other things. There was a group of people sitting there who were, I think this is the group of people who later on started doing magic tricks together. and they're sort of closing themselves up, and they would just sort of hang around and have the experience. They would tell stories. I would sort of peek in and see what people were doing, and all manner of things. One person actually I saw near the last day, one person told me that he had stayed in the project for 6 hours the night before. And he was just sitting there and waiting for people to come by, and he'd call them in, and they would just have these deep, heartfelt conversations. And he said that something about the mirrors reflecting himself back to him made him feel very introspective. And so he was back that night for another round. But the biggest thing for me is it sparked a lot of curiosity. So just like I was hoping, people had questions. So this person is, I don't know, I know what it says because I listened to it before, but he asks, what's the meaning of the project? And she's about to ask how many reflections you can see. And they just wanted to know things. And even better, everybody had follow-up questions. So instead of, they would say, what's it about? And I would say an unsolved math problem. They say, oh, what's the problem? And then I'd tell them about the conjecture, and maybe they would say, what's a polyhedron? Or they would say, oh, well, why can't you always do it? Or what's an example where you can't? Or couldn't you just try this? And it was very interesting. They were very engaged, and they just behaved like you would always hope your best students would, of just bringing this curiosity and want to know more. And to me, this is exactly what made the project a success. Okay, so what would I like you to take away from this talk? Well, so some things that I learned that I think was very good for me. If you ever want to do something like this, connect to your local art community. Artists, our local artists anyway, are just so enthusiastic about collaboration and learning and connecting. And I found so many people willing to come work with me, give me advice, and they were interested in mathematics. It was really a great connection to make. Also, I think it's good to introduce your students to the physical aspects of mathematics. So for example, in building this dodecahedron, this person, Wizard, who made the vertices for us, he said earlier, it's interesting that you chose a dodecahedron because those aren't rigid. All the icosahedron is, but the dodecahedron isn't. And I thought, gosh, it's really true. It kept sagging. Our models would sag. And of course that makes sense if you think about it, because the icosahedron has triangle faces and those are rigid, but the pentagon faces can sag. And so that's what was happening. And so these are the sorts of things that you can learn just by playing with physical models. And I guess the last thing is be bold. This was a really big project. This was way more than I expected. And I had no idea what I was getting into, but it was so worth it. And it all came together. So yeah, so be bold, give it a try. All in all, we had about 80 volunteers. There were 35 volunteers from our university, faculty, and students, and some staff members. There were about 50, there was about 50 volunteers from the community. And each night that we got together, so every Monday night and every Saturday day, we got together at CoLab to work on the electronics, or the sort of external part, the skin of it. And each time we got together, it was a different group of lovely people, like the whole community coming together. So here's Erica. She's from another university, San Diego State University. She's an art and computer science major, I think. And then here's Ross and Stephen. Those were the solderers for us. Sean is from the community. She was in information technology. This is Max, the person who did all our electronics. He's a Sony engineer. Susie Babka is a professor in theology at University of San Diego. Eduardo is a engineering student. He's just graduated. Karen Tang, she just came down for the day from Los Angeles and showed up and said, hey, can I help? And here's Ben Ciotti. He's a grad student at University of California, San Diego, another university in town. Paul's a community member. Sojana is a lovely woman from Serbia who wanted to join so that she could meet people. So really, it just brought together so many people in the community. And I'd like to acknowledge and thank them. It would never have happened without them. So here they are. Thank you so much to them. And thank you so much, everybody, for listening to my story.
So thank you, Professor Hoffoss. I think there is no question from participants. So let me thank Professor
I can't
Hoffoss.
hear you. If you're saying something, I'm sorry that I can't hear you.
Yeah, can you hear me now?
Uh-oh, this is not good. Dr. Ali, I can't hear you speaking. I don't know what to do. I see that you're unmuted, but I can't hear what you're saying.
Can you hear me now?
Is there something I could do for that? Maybe I can quit things. Okay. Well, I would love to answer questions. I can't hear what you're saying, but maybe I can read some things from the chat. So let's see if there's any questions. Lots of good mornings. Good morning, everybody.
Yeah, can you hear me?
Well, thank you so much for the nice
I
comments.
audible?
I appreciate that. Oh, I'm glad you found this story interesting. That makes me happy. Okay, if you have other questions, I'm sorry that I can't here to answer them, but I would be happy to if you wanted to contact me by email. We could continue this sort of conversation.
So thank you very much, Professor.
Thank you so much. I'm so sorry to not be able to do this, but I guess that's the challenge of technology.
The talk was very informative and very inspiring, especially for the
Click on the arrow next to
young.
your microphone, unmute. Yeah, so thank you for that advice. So select a speaker.
Yeah.
MacBook Air speakers, okay. What if I unplug the external? Let me see if that makes a difference. Can I hear? Can you say something?
Yeah. Can you hear me now?
Unmute my speaker. No, I can't. I've tried the same as system and MacBook Air speakers, and
so anyway,
oh, there you are.
let me thank Professor Hoffoss for a very nice and informative talk, and sharing her project and the details and how the idea came to her, and how it is transformed into reality as a working model. She is an expert of modeling the life situation, and it was very inspiring, especially for the young students. You must have seen how can you transform your imaginations into reality using mathematical principles. And there is a lot to do in mathematics beyond textbooks. And I mean, best example you have given, that the reflection that I mean, the people outside the mathematical community, what do they think about us? Asking the simple question when they come to know that we are professors, that what is the biggest number we can think of? But there is a lot beyond that. And this is a clear message to the non-mathematics audience, and that is the real art and beauty of mathematics. So thank you very much. And I once again I must apologize. I forgot to mention about one of my ignorance, that I by mistake I mentioned the affiliation of Professor Hoffoss as University of California, San Diego. It should be read as University of San Diego in California. So I apologize for this mistake. Later, I corrected also it in several notifications. So thank you once again, Professor Hoffoss, And thank you everyone for this.
So I've gotten my sound now. So if anybody
So
had a question.
yeah, I must add to this that if you want, if you are interested in know more about this project, she has published this project in very detail in Notices of American Mathematical Society. So you can have a look of that article. You will know more about this project. So thank you, everyone. Thank you for joining us in this room. And the next session will be on 4th, and that will be the last session. It will start at 10 o'clock. The speaker is Professor Shigeru Kanematsu from Kyushu Institute of Technology, Japan. So thank you very much. Thank you once again.
Thank you so much.